Welcome to normal probability distribution 6-4, the central limit theorem. Key concepts. The central limit theorem allows us to use a normal distribution for some very meaningful and important applications. Given any population with any distribution, uniform, skewed, or whatever. If you remember, uniform distribution looked like this, and it went from 2 to 5 seconds. And this was uniform because it's all the same height. And then we have skewed. We could have something that looks similar to a normal distribution, except it's skewed to the left. Those are not normal distributions, but using the central limit theorem, you have a population, you take some samples from that population, and you find the mean of each sample. The distribution of sample means can be approximated by a normal distribution when the samples are large enough with n greater than 30. And there are some special cases where you might need to use more than 30, but it is rare. If we look at figure 6-21, this is not a normal distribution. We can see that it doesn't look anything like a bell-shaped curve. This is the original data. This is a histogram of the depths in kilometers of 1,392 earthquakes. This histogram shows that those depths have a distribution that is clearly not normal. On the right, we have a histogram of 100 sample means. We took 100 samples from the population. We found the mean of each sample, and each sample had 50 earthquake depths. We made a histogram, and we've approximated a normal distribution because n is equal to 50. It's not perfect, but it's pretty good compared to what it was. We couldn't use normal distribution here, but here we can use the normal distribution. The interpretation. The original earthquake depths depicted in figure 621 have a skewed distribution, but when we collect samples and compute the mean for each of the samples, those sample means tend to have a distribution that is normal. We can take this data and turn it into something like this using the central limit theorem. For all samples of the same size, this is the sample size, n is greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with mean mu and standard deviation sigma over the square root of n, where n is the sample size. We have to be given either the population with any distribution. We have to know the mean and the standard deviation, and that these are simple random samples, all of the same size, and that we select from the entire population. If all possible simple random samples of size n are selected from a population with mean mu and standard deviation sigma, the mean of all the sample means is denoted by mu sub x bar, and the standard deviation of all sample means is denoted by sigma sub x bar. What does that mean? If we have a bunch of samples and we take the mean of the samples, the mean of the samples is equal to the mean of the population. That's pretty significant. And the standard deviation of the mean of the samples, sigma sub x bar, divided by the square root of n. And sigma sub x bar is called the standard error of the mean and is sometimes denoted as SEM, standard error of the mean. Practical rules for real applications involving a sample mean x bar. Again, we have our requirements. Either the population has a normal distribution or the sample size is greater than 30. The mean of all the means mu sub x bar is equal to the mean of the population. The standard deviation of the sample means is equal to the original standard deviation of the population, but we have to divide it by the square root of the sample size. And our z-score changes this a little bit. Remember, for population, we had z is equal to x minus mu over sigma. We're given a problem. We have to check the requirements. When working with the mean from a sample, verify that the normal distribution can be used by confirming that the original population has a normal distribution, or the sample size of each sample is greater than 30. We have to figure out if we have an individual value or we have a mean of a sample. First, determine whether you are using a normal distribution with a single value x or the mean x bar from a sample of n values. When working with an individual value from a normally distributed population, we use our z. But if we're talking about the mean from a sample of n values, we need to use the value sigma over the square root of n for the standard deviation of the sample means. And that changes our z. Instead of sigma, it would be sigma over the square root of n. And instead of x, which is one value, we get the mean of the samples.